All right, for question 1, we were asked to find the correct internal force sign conventions we use in the course. There wasn't much analysis to do here. It was more just remembering what we had learned, the process you could use. Think of a bar, make a cut, draw the axial or normal force and the moment. We know that the normal force goes directly out and the moment is concave up. Combining the two different sides, here, that's not working, and the other side, we get that the answer is C, where both sides are concave up and both normal forces are facing directly outward. Moving on to question 2, we are asked which of the following material properties is critical for the situation in which the airplane is experiencing excessive wing deflection. The two ideas to know here are the definitions of stiffness and strength. Stiffness being the resistance to elastic deformation, with high resistance, high stiffness meaning low deformation, and low stiffness meaning high deformation. With strength, it is the stress before breaking, with high strength equaling to high stress and low strength equaling to low stresses at breaking. We see that the wings are not breaking, but instead deforming intensely, elastically, so that would mean this is a issue of low material stiffness. Moving on to question 3, we are asked when yielding occurs, the material will, and this just needs to know the definition of yielding, which is the stress amount that turns a material from undergoing elastic deformation to plastic deformation. Beyond the yielding point, an object will not return to its original shape. Thus, looking back at the questions, I chose D as the stresses beyond yielding will generate permanent deformation. The fourth question, we are given a variety of different loading situations and asked which could generate normal stress. The 4 different types of loading that we were given and different arrangements, but were the transverse force, the axial loading, bending moment, and torsion. We know that the transverse forces result in shear as they apply forces across the parallel to the cross section. We know that axial loading is perpendicular to the cross section and thus will result in normal stresses. We know that the bending moment results in normal forces as it creates tension and compression. And we know that torsion will only create a shear stress, which relates to the distance from the center. Thus, you can go through all the answers and select any of the loading cases in which axial loading or bending moment was used. In our case, that applies to a lot of the options. The ones that include those two are B, C, E, F, H, I, J, K, L, M, N, and O. Moving on to question 5, the longer answer questions. We are given a situation in which 2 materials of different cross-sectional areas are between a movable structure, and as the objects are heated, we are asked to find at what temperature they will break. The first step for this is to calculate the modulus of elasticity for A from the graph that we are supplied. Using the equation rise over run, and using the 0.002 offset that you do to find the yielding stress. we can get that 210 over, to get the fracture stress. Sorry, that's just to get E. We get that 210 over 0.003 will be equal to 70 gigapascals. For material B, we were not given this in the question, but it was meant to be given, and in class we were told this value was 200 gigapascals. We then set up the equations and the geometric conditions. We know that the total change in length is going to be equal to 0 because they are stuck between this immovable structure, and thus the total deformation of 0 will be equal to the change in length of material A due to heat, the change in length of material B due to heat, and then the changes in length of AC. Probably could just write AC helps define it. AC, which is material A, and BC, which is material B, due to the compression. Some important equations to know are that the change in length due to thermal expansion is alpha, the thermal coefficient, and multiplied by the change in temperature times length. And then due to compression or tension, any normal forces, the change in length will be the force applied times the length divided by the cross-sectional area times the modulus of elasticity. It's important to know what compressive forces will be applied to the materials in order to solve for the compressive change in length and the stresses that arise. So creating two free body diagrams and two cuts in our material, we can solve for PA and PB, which are the forces experienced by material A and material B. And we realize that they're equal to each other and also equal to the opposite of the reaction force at the wall. Next thing we do is solve for the failure force, as it is the last unknown in our situation. We see from the graph that the ultimate stress is 240 megapascals, and we know that the area is 0.0005 meters. So we find that the force, the braking force, is going to be 120,000 newtons. From there, it's all just algebra and plugging in the known variables. So plugging in all these variables and rearranging, we get to the point where the change in temperature will have to be equal to 165 Celsius, and that corresponds to a rise in temperature. This makes sense as the thermal expansion, as the temperature rises, it will make the object expand, which will thus create compressive forces on the material. So the signs appear to match. Moving on to the final few questions, given a new setup, we are asked to find out a few different values about this system on the right. So for the first part of the question, we are asked to find the factor of safety against yielding for a bar when P, the load on the object on the right, is equal to 62 kilonewtons. The first important part is to set up a free body diagram for the forces on BDE to be able to solve for the force BY. Okay, perfect. So in order to solve for the force BY, we need the force, need the force BY. And to do that, we can use the moment about E. So by using the moment about E, we know that the P force is 65 kilonewtons, multiply that by the distance of 0.45 meters, and then subtract BY times 0.2 meters, set that equal to 0. we get that BY is equal to 146,250 newtons. So to find the factor of safety, we can, sorry, I skipped a step. We need to calculate the related stress in order to calculate the factor of safety. To calculate the related stress, we can use the equation that stress is equal to the force over area. Rearranging that to get stress times area is, sorry, that equation works perfectly. So doing the force over the area, 146,250 newtons over 0.001 meters, we get a value of 146,250,000 pascals. Calculating the FOS from there, we're given that the allowable stress was 210 megapascals. Dividing that by 146.25 megapascals, we get a value of 1.463, which is above failure. The 210 megapascals, again, comes from the previous question. Moving on to part C, we were asked what is the deflection of point B with force 62 kilonewtons applied. So we use the simple equation, the change in length is equal to pli, force times length over area times modulus of elasticity. In the previous question, we had solved the modulus of elasticity, and we know that P is the reaction force, which is going to be equal and opposite. So we just plug in all the unknowns into this equation, and we get the value negative 0.00073,125 meters. This makes sense to be a negative number because the force on this beam will be compressive, and thus the change in length will be negative. All right, and the final question that we are asked is to calculate the simple shear stress experienced by pins A and E. To do that, first I wanted to draw a free body diagram of both the pins, with pin A on the left and pin E on the right. We had to solve for the reaction force EY on pin E, which we got as negative 84,250 newtons. Because of the double shear, we realize that the shear experienced is half of this value on both of the pins. So for pin A, it is 73,125 newtons, and for pin E, it is negative 42,125 newtons. The final step is to plug those into the shear equation with tau equals V over A, which is the force over the area. Doing so for A gets a 103 megapascals, while doing this for E gets negative 59 megapascals. We were also given an extra credit question in which we were asked to find the change in cross-sectional area. In order to do this, we use the equations for Poisson's ratio of negative lateral strain over axial strain, where strain is equal to the change in length over L. Combining those two equations, we can solve for the lateral strain using the Poisson's ratio times the change in length, which was solved in the first section, divided by the overall length, and we get this value 0.00056412. Using the lateral strain, we then apply it in both directions to find the total change in area. So applying it to the side that is 0.02 meters long, we use the E lateral times 0.02 and add the original length of 0.02. Then for the second direction, we use strain lateral times 0.05 plus the original length of 0.05 meters, and we end up with these two long decimals. Multiplying them together gets 0.001, which is what we had before as the area, but it's a little bit bigger as it's 0.001001205 meters squared. Thank you.